So in this video, we're going to talk about a somewhat infamous type of Calc 2 problem. And this has to do with pumping water out of a container, or pushing or lifting water out of a container, if you will. Now, these problems are approached using a fundamentally different way of thinking than we applied in the chain and bucket problem. In the chain and bucket problem, we thought of the chain and bucket as being essentially a single object whose weight, whose force was varying as we lifted the chain and bucket out of the well. But the approach to these lifting problems is traditionally quite different to make them easier to calculate and easier to set up and conceptualize properly. So let's go through this example. Consider the problem of trying to pump all the water out of a cylindrical tank which has been positioned with its circular bottom on the ground. So let's go ahead and let's draw for ourselves a cylindrical tank positioned with its circular bottom on the ground. Now, even though the tank itself is 4 meters tall, so I will indicate x equals 4 and x equals 0 here. Those are the coordinates which occurred to me before anything else. The tank is only filled up with water to a height of 3 meters. So I'll note that as well. I'll put a little blue circle here, a little bit of a surface of water here at the location x equals 3. So the question is, how much work would need to be done to actually lift all of this water out of the tank, assuming that the tank has a radius of 2 meters from center to rim? Here is my picture. The idea is this. The idea is that we are going to consider this full volume of water, and then we are going to take our bread knife and slice this volume of water. We are going to slice it up very similar to how we sliced up volumes of solids of revolution when we were calculating those volumes. Then we are going to identify for each individual slice what would be the work done to move that one slice up and out of the tank. What would be the work done to move that one slice? Then we will use integration to take the sum total of all the work that needs to be done to move all the slices. So, here's the idea. Take some random slice of the object at some random height x. Maybe I'll just put my random height x right here in the picture. Find a formula f of x for the force that would be required to counteract the force of gravity and lift that slice. So here we go with a little teensy weensy slice here, a little slice here at x. Now here's the idea. The force that we would need to exert on that slice is the same as, in magnitude, as the weight of the slice. We're trying to counteract the force of gravity, and the weight of an object represents the force of gravity. Now, the weight of an object is equal to its mass times the acceleration due to gravity. And the mass of an object can be found by taking its area/volume, depending on whether you're dealing with a 2D or 3D object, taking its area/volume and multiplying that area/volume by the acceleration of gravity, and multiplying that by density, by the density of the water, because volume times density will give you the object's mass. So if we can find the area of this slice at position x, if we can find the area of the slice at position x, then we can multiply that by the acceleration due to gravity, which is usually called g for short, and we can multiply that by the density of water, which is usually called rho for short. A of x times g times rho would be the weight required to lift that one slice out of the tank. Now let's analyze this slice at position x. No matter where we take this slice of water, The slice will always have exactly the same shape and size. Every single one of these circular slices is a circle of radius 2. So the area is pi times the radius squared, pi times 2 squared. Therefore, the force that would be required to lift this two-dimensional slice located here at position x would be the area of the slice times the acceleration due to gravity times the density of water, 4 pi g rho for short. That concludes step 2. Step 3. Okay, for this one slice, we figured out the force that would need to be exerted on that one slice. We also need to figure out the distance that would be traveled by that one slice, because force times distance is work. So that would be the work done to lift that slice if we take the product. Now this is where I would go back to our drawing. In order to escape this tank, I need to lift this slice at position x up to a height of position 4, which is where the top of the tank is located. So in order to do that, I would need to travel 4 minus x, a total of 4 minus x units, to get from where the slice is currently located up to a position of x equals 4. I still have 4 minus x units left to go. So the distance traveled based on that image is the height of 4, take away the height of the slice. Now, the work done, let me put this in parentheses, the work done to lift the slice at position x is equal to the product of the force and the distance traveled. So that would be 4 pi g rho force, distance traveled, for take away x. To find the total work done, we're going to use integration. We are going to take the sum total of the work done to lift all of these slices. But what should our limits of integration be? We have to be careful. The limits of integration should not be from 0 to 4, because there's no water to lift up here at x equals 4. The water that we have to lift only exists between the limits x equals 0 and x equals 3. So let's set our limits to be, here is the lowest slice of water that we need to lift, x equals 0. And here is the highest slice of water that we need to lift, x equals 3. And so we can integrate this expression with respect to x to find the total work done. And I will leave that to you as an exercise. You can do it simply by using constant multiple rule. 4 pi g and rho are all just numbers, and so then you can integrate from 0 to 3 this expression 4 minus x in the back using the standard process.